Good day everyone, we are Team Gadolinium and today we will be discussing about concepts related to electrochemical methods of analysis. To start with our discussion, let us first discuss electrochemistry. Electrochemistry is the study of how electricity is related to some chemical reactions. It also deals with the movement of electron in an oxidation or reduction reactions within a polarized electrode surface. In electrochemistry, the analyte of interest is oxidized or reduced at specific potential in which the current being measured is proportional to the concentration. In oxidation-reduction reactions, electrons are transferred from one reactant to another. One of the examples is oxidation of iron 2 ions by cerium 4 ions. The reaction is described by the equation you can see on your screens. In this reaction, an electron is transferred from Fe2+ to Ce4+ to form Ce3+ and Fe3+ ions. A substance that is said to have strong affinity for electrons, such as in this case the cerium 4+, is called the oxidizing agent or an oxidant. On the other hand, a reducing agent or reductant is a species that donates an electron to another species. In this case, our reductant is the Fe2+. To fully describe the chemical behavior of this equation, we can say that Fe2+ is oxidized by Ce4+, and likewise, Ce4+ is reduced by Fe2+. Before we can continue with our discussion regarding redox reactions, let us first have a quick discussion on how to balance redox equations. To practice, let us consider the equation you can see on your screens. The first thing to do is to write and balance the two half reactions. Specifically for permanganate, we write its half reaction, such as this one. To account for the 4 oxygen atoms on the left side of the equation, we will add 4 hydrogen oxide on the right side of the equation, and then to balance the hydrogen atoms, we will provide 8 H+ on the left side of the equation. Another thing to consider when balancing redox equations or reactions is their charges. We also have to balance their charges, and in this case, we will add 5 electrons on the left side to have a positive 2 charge on both sides of the equation. For the half reaction of NO2-, we have this equation. We have to add 1 hydrogen oxide on the left side to supply us the needed oxygen to balance the equation. We also have to add 2 H+ on the right side. To balance their charges, we have to add 2 electrons on the right side. Now that we have two different equations, prior to combining them, we must multiply the first equation by 2 and the second one by 5 so that the number of electrons that was lost will be equal to the number of the electrons we gained. Adding the two equations, we will have this equation, and this equation rearranges to this balance equation. Some of the redox reactions can be compared to some of the acid or base reactions in such a way that they are somehow analogous to the Bronsted-Lowry concept of acid or base reactions. In both reactions, one or more charged particles are transferred from a donor to an acceptor, electrons for oxidation or reduction reactions, while protons for neutralization. In Bronsted-Lowry reactions, when an acid donates a proton, it becomes a conjugate base that is capable of accepting proton. By analogy, when a reducing agent donates an electron, it becomes an oxidizing agent that can accept electron. With this concept, we can write the generalized equation for redox reactions such as the one given on the screen. This equation, B oxidized, which is the oxidized form of the species B, accepts electrons from A reduced to form the new reductant given by B reduced. At the same time, A reduced, having given up electrons, become an oxidizing agent, A oxidized. We can fully understand oxidation or reduction equilibria by measuring potentials of electrochemical cells in which the two half reactions making up the equilibrium participate. An electrochemical cell consists of the two conductors, which are called electrodes, each of which is immersed in an electrolyte solution. These solutions must be different and separated to avoid direct reaction between the reactants, and the most common way to do this is the use of salt bridge between the solutions. In the figure you can see on your screen, salt bridge was used to isolate copper sulfate solution and silver nitrate solution. The conduction of the electricity from one solution to the other occurs by the migration of potassium ions in the bridge in one direction and chloride ions in the other. If the circuit is open, there will be no net reaction. The voltmeter measures the potential difference or the voltage between the two electrodes. This voltage is the measure of the tendency of the cell reaction to proceed toward equilibrium. In the figure you can see on your screens, the cell is connected so that the electrons can pass through a low resistance external circuit. In the figure, metallic copper is oxidized at the left-hand electrode, while the silver ions are reduced at the right-hand electrode, in which electrons flow through the external circuit to the silver electrode. As this reaction continues, the cell potential initially at 0.412 volts, the circuit is open, decreases continually and approaches 0 as overall reaction approaches equilibrium. A cell with 0 voltage does not perform work. Cathode is the electrode at which the reduction reaction occurs, while the anode is the electrode where oxidation reactions occurs. Some of the examples of the typical cathodic reaction can be seen on the screen. A desired reaction can be forced to occur by applying suitable potential to an electrode made up of unreactive materials such as platinum. On the other hand, some of the typical anodic reactions can be seen on the screen. Electrochemical cells are either galvanic or electrolytic and can also be classified as reversible or irreversible. Galvanic cells stores electrical energy. The reactions of the two electrodes in such cells tend to proceed spontaneously and produce a flow of electrons from anode to cathode by an external conductor. The figure on the screen shows a galvanic cells that shows a potential of 0.412 volts when no current is drawn from it. The silver electrode is positive with respect to the copper electrode, while the copper electrode is negative electrode. This electrode is a potential electron source to the external circuit upon the cell being discharged. The figure on the screen is also a galvanic cell but is now under discharge, in which the electrons move through the external circuit from the copper to silver electrode. The silver electrode serves as a cathode since the reduction of silver ions occurs there, while copper electrode serves as an anode since the oxidation of copper occurs there. The net reaction during this discharge is called a spontaneous cell reaction. On the other hand, in electrolytic cell, it requires an external source of energy to operate. A cell can be used as an electrolytic cell by connecting the positive terminal of an external voltage source to the silver electrode and the negative terminal to the copper electrode as shown in the figure. Since the negative terminal of the voltage source is electron rich, electrons flow from this terminal to copper electrode, where copper 2+ is reduced to copper. The current in the cell is sustained by the oxidation of silver to silver ions at the right-hand electron, in which it produces electrons that flow to the positive terminal. Note that the direction of the current in an electrolytic cell is the reverse of that of the galvanic cell, as well as the reaction of the electrodes. Silver electrode is forced to become the anode, while copper electrode is forced to become the cathode. The net reaction when a voltage is higher than the galvanic cell voltage, or the net reaction in an electrolytic cell, is the opposite of the spontaneous cell reaction given by the equation you can see on the screen. Electrochemical cells can also be classified as reversible and irreversible cells, in which in reversible cells, the direction of the electrochemical reaction is reversed when the direction of the electron flow is changed. On the other hand, in irreversible cells, changing the direction of the current causes entirely different half reactions to occur at one or both electrodes. Shorthand notation can be used to describe electrochemical cell, and this electrochemical cell can be described by this equation. The single vertical line indicates an interface at which a potential develops between the copper electrode and the copper sulfate solution. Double vertical lines represent the two phase boundaries, one at each end of the salt bridge. In each interfaces, there is a liquid junction potential that results from the differences in the rate at which the ions migrate across the interfaces. This figure shows the movement of the charge carriers in galvanic cells undergoing discharge. These charges can be transported in the electrochemical cell by three different mechanisms. One, electrons carry the charge within the electrodes as well as the external conductor wherein the current is in opposite direction to electron flow. Next, the charge carriers within the cell are the anions and the cations. In the left-hand compartment, the copper is oxidized to copper ions, and it moves away from the copper electrode, while the anions such as the sulfate and hydrogen sulfate ions moves towards the electrodes. In the salt bridge, the chloride ion moves towards the copper compartment, while the potassium ion moves to the silver compartment. In the right-hand compartment, the silver ion moves towards the silver electrodes, while the nitrate ions moves toward the black solution. And lastly, the ionic conduction of the solution is coupled to the electronic conduction in the electrodes by the reduction reaction that happens at the cathode and the oxidation reaction that happens at the anode.
So I will now be discussing about electrode potentials or thermodynamic potential. When measured for purposes of electrochemistry, a potential reflects the driving force for a specific type of charge transfer process, so namely the transfer of electrons between redox reactions. So, considering the nature of potential in this context, it is clear that the potential of a single half cell or a single electrode can be measured. Transfer of electrons requires both a donor and recipient. So, in this case, a reductant and an oxidant, respectively. Instead of a half cell, potential may only be assessed relative to that of another half cell. So, it is the only difference in potential between two half cells that may be measured, and these measured potentials are called cell potentials. So, it is defined as E cell is equals to E cathode minus E anode, where E right and E left are the electrode potentials of the right hand and left hand electrodes, respectively. So this equation is valid when the electron potential is absent or minimal. So throughout this topic, we will assume that liquid junction potentials are negligible. So I will now proceed to the sign convention for cell potential. So an electrochemical cell may be prepared by combining any two half cells. So such cells and half cells are conveniently described by an abbreviated notation together with appropriate conventions so that the convention will correspond to the chemical reaction taking place in the cell. So moreover, the conventions used for the cells must be compatible with other thermodynamic conventions. The following notations are used by convention for describing cells and half cells. So first one is the half cells written in the sequence electrolyte represents oxidation, and the sequence is electrode, it means reduction. So examples are here in this figure. You can see the oxidation and reduction. So note that gas electrodes or oxidation reaction electrodes have an inert metal, which is platinum, as the electron carrying medium. So second one is a complete cell is written such that left hand side represents the oxidation reaction, half cell, which is the anode, and the right hand side represents the reduction half reaction half cell, which is cathode cell, as shown below. Vertical line in the middle means that the two solutions are in direct contact. So if, however, contact between the two solutions is made through a salt bridge, two vertical lines are placed between the two electrolytes as shown below. But we can simplify it by this, like the half cell of zinc and the half cell of copper. So using the example for number 2, we can actually calculate the cell potential for this voltaic cell of the half cell of zinc and half cell of copper. So here we have the electropotential values for the zinc half cell and the copper half cell. For the zinc, we have negative 0.76 volts, and for copper, we have positive 0.34 volts. So we can now input these values using this equation. The copper half cell has the more positive standard electropotential value and will undergo reduction, so it will be the cathode, and the zinc half cell has the more negative standard electropotential value, so it will undergo oxidation. It will be the anode. And now we have the value of the cell potential for this voltaic cell, which is positive 1.10 volts. The positive sign indicates that this is a spontaneous reaction. So next one, before the third one, we have EMF, which is the electromotive force of a cell, or cell EMF is the maximum potential difference between the two electrodes of a cell. So for the third one, the sign of the electrodes are opposite to those used for electrolytic cells. So electrochemical cells, anode is negative and cathode is positive, while in electrolytic cells, anode is positive and cathode is negative. So For the fourth one, the electrode where an electron is released, oxidation takes place, is written on the left side and is the anode, and the electrode is written on the right side. An EMF will be called positive if there is a tendency for electrons to be driven through the external circuit from left to right. So if the cell is written such that reduction is taking place at the left hand electrode, the EMF of the cell will be negative. And for the fifth one, for calculating the cell potential, the reduction potential is used along with the relation. And the last one is if the EMF of the cell has a positive value, the cell reaction is spontaneous, just like the example a while ago. The value of the cell potential is positive, so it is spontaneous. So if the cell works is in such a way that an electron is released at the left electrode and is driven through the external circuit from left to right, the cell reaction will be spontaneous. And that is all for the sign convention for cell potentials. So let us now proceed to the standard hydrogen reference electrode. To simplify the collection and sharing of potential data for half reactions, the scientific community has designated one particular half cell to serve as a universal reference for cell potential measurements, so assigning it as a potential of exactly 0 volts. So this half cell is the standard hydrogen electrode, and it is based on half reaction below. So a standard hydrogen electrode, it usually contains an inert platinum electrode immersed in precisely 1 molar of aqueous hydrogen and a stream of bubbling H2 gas at 1 bar pressure, all maintained at temperature of 298 K. So the assigned potential of the standard hydrogen electrode permits the definition of a conveniently measured potential for a single half cell. So the electrode potential, which is the EX for a half cell, X is defined as the potential measured for a cell comprised of X acting as cathode and the standard hydrogen electrode acting as an anode. So we have this equation, which is the E cell is equals to EX minus E she, so 0 volts based on its definition. So we have E cell is equals to EX. When the half cell X is under the standard state conditions, its potential is the standard electrode potential E naught X. Since the definition of cell potential requires the half cells function as cathodes, these potentials are sometimes called standard reduction potential. So this approach to measure electrode potentials is actually illustrated in this figure on the right side, which depicts a cell comprised of an standard hydrogen electrode connected to a copper half cell under standard state conditions. So a voltmeter in the external circuit allows measurement of the potential difference between the two half cells. So since copper half cell is designated as the cathode in the definition of cell potential, it is connected to the red or the positive input of the voltmeter, while the designated standard hydrogen electrode anode is connected to the black, which is the negative input. This connections ensures that the sign of the measured potential will be consistent with the sign conventions of electrochemistry. A cell potential of positive 0.337 volts is measured. So we have E naught cell is equals to E naught copper, which is equals to positive 0.337 volts. So the tabulation of the E naught values for other half cells measured in a similar fashion are available as reference literature to permit calculations of cell potentials and the predictions of the spontaneity of redox processes. So let's now proceed to electrode potential and standard electrode potential. So electrode potential is the potential of an electrode is known as the potential of a cell consisting of the electrode concerned acting as cathode and the standard hydrogen electrode acting as an anode. So the cathode is always reduced while the anode is oxidized. So standard electrode potential is a measurement of the potential for equilibrium. So there is a potential difference between the electrode and the electrolyte called the potential of the electrode. When unity is the concentration of all the species involved in a semicell, the electrode potential is known as the standard electrode potential. So, as for other thermodynamic quantities, the standard cell potential E naught cell is a cell potential measured when both half cells are under standard state conditions, which is actually 1 molar concentration, 1 bar pressures with 298 K temperature. So we have this equation. We have E naught cell is equals to E naught cathode minus E naught anode. And that is all for the electrode potential or thermodynamic potential.
Hello, I am John Rabel of Ronda, and I will be discussing the effect of concentration on electrode potentials, the Nernst equation. The Nernst equation calculates electrochemical cell potential at any known temperature, pressure, and concentration. The equation relates the reduction potential of the cell at a non-standard condition to that of the standard conditions. When a redox reaction occurs in a galvanic cell, the concentration of the reactants decreases as they are consumed, while the concentration of the products increases due to more product formation. The cell potential decreases until equilibrium is reached and a zero cell potential is reached. The Nernst equation is derived from Gibbs free energy under standard conditions, which is represented by this equation. Delta G is also related to E under general conditions, standard or not, via this equation right here, wherein N is the number of electrons transferred in the reaction, and F is the Faraday constant, and E is the potential difference. Under standard conditions, delta G can be written as this equation, wherein E naught is positive, the reaction is spontaneous, and E naught is negative, the reaction is non-spontaneous. From thermodynamics, the Gibbs energy change under non-standard conditions can be related to the Gibbs energy change under standard equations via this equation, wherein Q is the reaction quotient, wherein Q is the same as the equilibrium constant expression K, except not necessarily at equilibrium. Substituting delta G and delta G naught into equation 4, we will get this equation right here, equation 5, and dividing both sides of the equation above by negative NF, we will result into this equation right here. We can further simplify this equation into rewriting it into the form of log 10. For historical reasons, the logarithm in equations involving cell potential is often expressed using base 10 logarithm, which changes the constant by a factor of 2.303. Now, multiplying 2.303 to the ideal gas constant and the standard temperature 298 Kelvin will result into this equation right here, which is the simplified equation. At equilibrium, delta G equals to 0 and delta G is equals to negative N times F times E, wherein delta E equals to 0. Substituting K equals to KEQ and equals to 0 into the Nernst equation, we have this equation right here. Equation 9 simplifies into log base 10, which was natural log was converted to log base 10, which rearranges to this equation right here, that the equation relates or indicates that equilibrium constant KEQ is proportional to the standard potential of the reaction. Considering the reversible half reaction, here, the electrode potential for this process is given by this Nernst equation right here. Practice example, write the Nernst expression of the following typical half cell reactions. You can write your answers on the MS Names comment tab section. And here are the answers of the following typical half cell reactions. The standard electrode potential, E0. In a galvanic cell, current is produced when electrons flow externally through the circuit from the anode to the cathode because of the difference in potential energy between the two electrodes in the electrochemical cell. Just like water flowing spontaneously downhill, which can be made to do work by forcing a water wheel, the flow of electrons from a higher potential energy to a lower one can also be harnessed to perform work. In the zinc-copper system, the valence electrons in zinc have a substantially higher potential energy than the valence electrons in copper because of shielding of the s electrons of zinc by the electrons in field d orbitals. Hence, electrons flow spontaneously from zinc to copper to ions, forming zinc to ions and metallic copper. As seen here, the potential difference of zinc and copper is 1.10 volts. The voltage of a galvanic cell depends partly on the identity of the reacting substances. The measured potential of a cell also depends strongly on the concentration of the reacting species and the temperature of the system. To develop a scale of a relative potential that will allow us to predict the direction of an electrochemical reaction, the magnitude of the driving force for the reaction, the potentials for oxidation and reductions of different substances are measured under comparable conditions. That is why chemists use the standard cell potential, defined as the potential of a cell measured under standard conditions. That is all. Standard potentials are measured in 298 Kelvin and 1 atm and in all 1 molar solutions. Standard electrode potential data are available for an enormous number of half reactions. Calculate the electrode potential of a silver electrode in a 0.0500 molar solution of sodium chloride using the standard electrode potential of the silver electrode, which has a value of 0.799 volts. The half cell reaction is represented by this reaction. First, we would like to calculate the concentration of the silver ion. But in this case, the concentration of chloride ions is given. So using the KSP value of silver chloride, we would like to calculate the concentration of silver ions from the KSP value. So rearranging the equation will result into this equation here, wherein the KSP is 1.82 times 10 raised to negative 10 divided by the concentration of chloride ions, which is 0.0500, which will equal to 3.64 times 10 raised to negative 9 molar. By substituting the calculated concentration of the silver ions and substituting it into the Nernst expression, since the silver ion is the only participating species in the half cell reaction, substituting it to the Nernst equation gives the equation of 0.799 minus 0.0592 times the log of 1 all over 3.64 times 10 raised to negative 9, which results to 0.299 volts of electrode potential in the silver electrode. Some limitations to the use of standard electrode potentials. Substitution of concentration for activities. One important limitation is that the Nernst equation is defined in terms of the activity of ions instead of their concentrations. Although it is easy to prepare a solution for which the concentration of sodium ion is 0.1 molar using sodium chloride just by weighing 5.844 grams of sodium chloride and dissolving it in 1 liter of water, wherein it's much more challenging to prepare a solution for which the activity of sodium ion is 0.1. For this reason, in calculations, we usually substitute concentrations for activities when using the Nernst equation. This simplification generally is okay for dilute solutions where the small difference between the activities and the concentrations are small. Effect of other equilibrium concentrations. A standard state potential tells us about the equilibrium position of a redox half reaction under standard state conditions. If one or more of the species in the half reactions are involved in other equilibrium reactions, then these reactions will affect the value of the standard potential. For example, Fe2 plus and Fe3 plus form a variety of metal ligand complexes with Cl ions, which explains why E naught of the Fe3 plus and Fe2 plus system is 0.771 in the absence of chloride ions, but is 0.70 and 1 molar of hydrochloric acid. Formal potentials. One way to compensate for using concentration and partial pressure in place of activities and fugacities, and to compensate for other equilibrium reactions is to replace the standard state potentials, E naught with a formal potential E naught prime. That is measured using concentration of 1 for ions and partial pressures of 1 for gases, and for specific concentration of other reagents. The table above here provides formal potential for Fe3 plus and Fe2 plus, Fe3 plus Fe2 plus half reactions in 5 different solvents as seen here. Applications of standard electrode potentials. Calculating potentials of electrochemical cells. We can use standard electrode potentials and the Nernst equation to calculate the potential obtainable from a galvanic cell or the potential required to operate an electrolytic cell. The thermodynamic potential of an electrochemical cell is the difference between the electrode potential of the right hand electrode and the electrode potential of the left hand electrode that is represented by this equation. For example, calculate the thermodynamic potential of the following cell and the free energy change associated with the cell reactions here. First, the two half reactions and the standard potentials are given here. First, we must calculate, using the Nernst equation, the electrode potential of the silver electrode, which is 0.799, its standard electrode potential, minus 0.0592 times the log of its 1 over its concentration, which is 0.0200, which equals to 0.6984 volts. Now, we would like to calculate the electrode potential of the copper electrode. 0.337 is its standard potential, minus 0.0592 divided by 2, which is the electrons transferred on the reaction, basing on this half cell reaction, times the log of 1 all over its concentration, which is 0.0200, which then equals to 0.2867 volts. We see from the cell diagram that the silver electrode is the right hand electrode and the copper electrode is the left hand electrode. So using this equation and substituting their values, the right hand electrode or the silver electrode is equals to 0.6984 minus the left hand electrode, which is the copper electrode, which is 0.28667, which equals to positive 0.412 volts. For its free energy change, the delta G for the reaction is given by this equation, wherein delta G is equals to negative N, which is the number of electrons transferred in the reaction, times Faraday's constant times the value of the E cell, which is 0.412. So negative 2 times the Faraday's constant, 96485 coulombs times 0.0412 volts, which equals to negative 79,503 joules or 18.99 kilocalories. Calculate the potential for the cell. You can write your answers on the comment sections on the MS Teams. In contrast to the previous example, however, the silver electrode is on the left and the copper electrode is on the right. Substituting these electrode potentials into the equation, wherein the right hand side is the copper electrode and the left hand side is the silver electrode, which equals to 0.2867 minus 0.6984, which equals to negative 412 volts. Thank you.
Now, let us discuss how to determine the standard reduction potentials experimentally. The standard reduction potential is the likelihood of a particular molecular atom to be reduced, or gain electrons. But how do we determine the standard reduction potential experimentally? Looking up the standard potential for hundreds of half reactions is actually easy. But it is important to realize that none of these potentials can be measured directly in the laboratory. First, it needs to have a galvanic cell which can conduct electricity using a standard hydrogen electrode or SHE. This is the reference electrode and the standard reduction potential is set as 0 for SHE. Then, the other side of the galvanic cell is set up with the material in question, for example, copper. Then, the standard reduction potentials are used to determine the standard cell potential. The standard reduction cell potential and the standard oxidation cell potential can be combined to determine the overall cell potentials of a galvanic cell. The equations that relate these three potentials are shown below. Next, when solving for the standard cell potential, the species oxidized and the species reduced must be identified. This is with the help of the activity series. It is a list of standard reduction potentials in descending order of the tendency for chemical species to be reduced. The species at the top have a greater likelihood of being reduced, while the ones at the bottom have a greater likelihood of being oxidized. Therefore, when a species at the top is coupled with a species at the bottom, the one at the top will become reduced while the one at the bottom will become oxidized. Below is a table of the standard reduction potentials. For our next topic, let's try to calculate the redox equilibrium constants. The equilibrium constants of an electrochemical cell's redox reaction can be calculated using the Nernst equation and the relationship between the standard cell and free energy. To calculate the equilibrium constant for an electrochemical cell, we need to know the following. First, the standard state potential for a cell, and the other one is the half reactions involved. With that, here's an example. Find the value of the equilibrium constant at 25 degrees Celsius for the cell reaction for the following electrochemical cell. For the first step, write the cell half reactions and determine the standard cell potential and the numbers of electron transferred. In this particular example, your standard cell potential is going to be 0.281 volts and the number of electrons will be 2. Next, substitute the values into the Nernst equation and solve for K. Take note that under standard condition, you may use either of the two equations. Use the values obtained and substitute to get your equilibrium constant. And for this particular example, our equilibrium constant is going to be 3.1 times 10 raised to 9. The next part will be the oxidation and reduction indicators. Redox indicators are chemicals which do not participate in redox reaction, but their color in oxidized and reduced form is different. Upon the addition of the titrant to the analyte, the color of the solution changes due to the change in oxidation state of the indicator indicating the endpoint. There are two types of oxidation and reduction chemical indicators, and these are chemical redox indicators and specific indicators. General oxidation reduction indicators are substances that change color on being oxidized or reduced. In contrast to specific indicators, the color changes of true redox indicators are largely independent of the chemical nature of the analyte and titrant, and depend instead on the changes in the electrode potential of the system that occur as the titration progresses. The half reaction responsible for color change in a typical general oxidation reduction indicator can be rewritten as this. Next, here's a list of potentials for several redox indicators. Now, let us move on to our second one, and these are the specific indicators. Starch is one of the most common specific indicator, which then forms a dark blue complex with triiodide ion. This complex signals the endpoint in titrations in which iodine is either produced or consumed. Another specific indicator is potassium thiocyanate, which is used in titration of iron 3 with solutions of titanium 3 sulfate. The endpoint occurs when the red color of the iron 3 thiocyanate complex disappears as a result of the significant decrease in the iron 3 concentration at the equivalence point.
The next report is all about the auxiliary oxidizing and reducing agent. So for the brief introduction, Linus Pauling in 20th century was first to study the redox titration to determine the ascorbic acid concentration using iodine solution. So for the analyte of redox titration, it must be in a single oxidation state. So these are the essential process or guide for the redox titration. First, dissolve the samples. Second is separate the interferences. And third is to convert all the analytes and mixture of oxidation state. So a sample containing iron is dissolved. The sample will contain iron 2 and iron 3 ions. So to proceed to the analysis of iron as a standard oxidant, we must convert all ions into iron 2 via the application of an auxiliary reducing agent. However, a standard reductant should be pre-treated with auxiliary oxidizing agents. So these are the pre-adjustment by auxiliary reagent diagram. Next is the pre-oxidants and pre-reductants. So pre-oxidants and pre-reduction should be easy to remove since those reagents may interfere with the titration, especially due to the unintentional interaction of the substance with the standard solution. So these are the list of chemical reagents used as a pre-oxidant and pre-reductant. So these are the list of good metals as a reducing agent. So zinc, aluminum, cadmium, lead, nickel, copper, and silver. This appears in the presence of chloride ions. So for the auxiliary reducing agent application, after the reduction of the analyte is established, the solid is manually removed and rinsed in water. The filtration of the analyte should be done afterward so that the granular and powdered metals will be removed. A reductor is an alternative for filtration. Within the reductor, the separated metal is held within a vertically positioned glass tube and was shown under a mild vacuum. For Jones reductor. So a Jones reductor is commonly exists in a diameter of 2 cm which can hold 40 to 50 cm column of amalgamated zinc. Amalgamation is a process in which zinc granules reacts with a solution of mercury which is established by the formula given below. So this is the setup for Jones reductor. So as we know, the zinc amalgam is one of the materials that is partnered with Jones reductor. So zinc amalgam is effective for reduction of pure metal and is essential in the reduction of hydrogen ions. So the reagent is a reducing agent. However, it is established as contamination with many zinc 2 ions. So by this, the importance of Jones reductor helps to establish chemical reaction with low to zero amount of hydrogen formation occurrence. So a granular metallic silver in a wood and a Walden reductor is held by a narrow glass column reductant. So note that the silver is not good as reducing agent unless other ions that can form silver salt of lower solubility like chloride are present. So another discussion for Walden reductor, a pre-reduction with Walden reduction is established by a hydrochloric solution of the analyte. So the silver chloride coating produced on the metal removed periodically via dipping of zinc stain into solution that covers the packing. So auxiliary oxidizing agent. So for the application of reducing agent, first we have the reagent sodium bismutate. So sodium bismutate is an oxidizing agent capable of converting ions such as manganate into permanganate. So in applying this reagent, it should be performed by taking the bismutate suspended from the analyte solution and boiling it for a few seconds or few periods. So the unused reagent will be removed via filtration. So the half reaction for the reduction of bismutate is given with the chemical reaction below. So next one is ammonium peroxydisulfate. It converts species such as cerium 3 to cerium 4, chromium 3 to dichromate, manganese 2 to permanganate. So this is the chemical reaction for ammonium peroxydisulfate. So the excess reagent can be decomposed by the means of boiling and established by the reaction given below. So next one is the sodium peroxide and hydrogen peroxide. Both sodium salts diluted salts of peroxides can be used as an oxidizing agent. So this is given with the chemical reaction below. So for the removal of excess reagents by boiling, um, next one is the application of standard reagent. So reagents used in redox titration. So for the reducing agents, these are the list of the chemical reagents that can be used. So the volumetric ratio of the standard oxidant and iron 2 solution is done with titrating 2 to 3 alicals of iron 2 and oxidants. The solution is commonly used in determination of the organic peroxides, chromium 6, cerium 4, molybdenum 6, nitrate, chlorate and perchlorate, and other oxidants. So those are the standard oxidants and iron to solution volumetric ratio. So for the thiosulfate is commonly used with the iodine intermediate in determining oxidizing agent with the half reaction given below. So thiosulfate loses 1 electron for each interaction. So for applying standard oxidizing reagent, application of standard oxidizing agents. So these are the reagents used in the redox titration. So potassium permanganate and cerium-4, the half reaction for permanganate ion and cerium-4 is parallel to one another. It is commonly established by this reaction. Cerium-4 in sulfuric acid is stable. Meanwhile, permanganate solution decomposes slowly and has occasional standardization. The mentioned cerium-4 solution doesn't oxidize chlorides and can be used in titrating HCl solution in analytes. Permanganate solution cannot titrate HCl solution unless slow oxidation of chloride ions is prevented since it consumes high amount of standard reagent. So, a change in color of permanganate ions is a good indicator. Permanganate is way cheaper than cerium-4 solution. Cerium-4 has a tendency to form precipitates. So for the next one is the general overview of electrochemical methods. First is the potentiometry. Potentiometry is an analytical technique in which analyzes the concentration of compound using the potential between two electrodes. So this is the diagram for the potentiometry. Um, potentiometry in potentiometry, electrical potentials are generated at the interference between a metal and its ions in solutions. So such potentials also exist when the different concentration of an ion are separated by a membrane that is semi-permeable in the ion. So as the reference potential, a constant voltage source is required to measure the electrode potential. The electrode with a constant voltage is referred to as the reference electrode, and the measuring electrode is referred to an indicator electrode. So, to calculate the cell potential, this is given with the formula below. Next one is conductometry. Conductometry is an analytical technique which analyzes ionic species and to observe the chemical reaction by studying their electron conductivity. It is commonly observed using conductivity meter or conductometric titration. So the recurrent conductometry was first used, but it has a disadvantage in terms of electrode polarization. So alternating current were used in assessing samples. So in conductometry, this is the diagram or the setup for the process. So conductometric method also helps with the determination of concentration of electrolytes within aqueous solution, which is given by the formula. So next one is voltammetry. Voltammetry is an analytical technique that observes the species by cancelling similar oxidation potential with one complete scan or cycle. In voltammetric analysis, controlled electricity will be applied to a working electron considering the time and the current produced by the system, commonly measured by an instrument potentiostat. So what is potentiostat? A potentiostat is a measuring tools which is capable of applying variable potentials to the working electrode relative to the reference electrode, like silver chloride, when measuring the current that flows as a result of the electrode reaction. So these are the several types of the analysis that can be used in performing voltammetry, which includes cyclic voltammetry, linear field voltammetry, square wave voltammetry, stripping voltammetry, alternating current voltammetry, pulse voltammetry, steady-state microelectrode voltammetry, hydrodynamic voltammetry. So on the record, the most frequent use technique is cyclic voltammetry, which assesses the potential over the time scale of seconds. So in contrast, the alternating current voltammetry assesses the potential over the time scale of milliseconds. As we know, in a redox reaction, the energy was produced by transfer of electrons from the species to another. So with the idea that redox reaction helps to establish the controllably produced energy by spontaneous reaction of two separate half reactions. So with this idea, the galvanic or the voltaic cell was promoted. And to elaborate, it includes two systems containing varied half reactions, and using a wire, electrons are derived from one system to another. So this is the setup for or the reaction within the galvanic cell. So as you can see, we have zinc anode and copper cathode. So for the parts of the galvanic cell, first the electrodes. These electrodes composed of two distinct types. So first is the anode, which is electrode in which oxidation takes place. So next one is the cathode, a type of electrode in which reduction takes place. So next one is electrolytes. So electrolytes are the substances that regulates the flow of electricity by means of ionic conduction. So that's all for my report. Thank you.